Good morning, everyone. Just 1 or more 2 minutes. I see people and okay, let's start with a brief introduction. Um, Good morning and welcome to today's webinar. It's the first webinar that C5 Lab does, and it's worldwide. Thank you for your presence. It is a pleasure to have you with us for this session. And this session is dedicated to the presentation of two projects developed with our researchers, focus on sustainability modeling and decarbonization pathways for the cement industry. Before we begin, a brief practical note. This session is being recorded, and please use the Q&A function that you have for the presentations to submit your questions, and we will address them together during our final discussion session. Just a bit introduction about C5 Lab. C5 Lab was established 5 years ago with the aim to bring cement in the industry, academy, and research organizations together to turn knowledge into impact. To do so, C5 Lab brings key partners from the cement and construction ecosystem in Portugal, including our associates, Simpor Cécio, Portuguese Cement Association, National Laboratory for Civil Engineering, and Instituto Superior Técnico, ensuring working that is both scientifically robust and industrially relevant for all the partners. Um, Let me now briefly introduce to you today's agenda. We will begin with an introduction by Professor Paulo Ferrão, who will provide a broader context for this work with a particular focus on sustainability modeling for the cement and concrete industry, and the first thoughts about that 5 years ago. Next, Melissa Bacatel and Francisca Puxa will present the two projects. The first one is about life cycle assessment model of the Portuguese cement sector, developed as a decision support tool for the both industry and public policy. The second explores the role of green hydrogen and CO2 capture in the decarbonization of the cement sector and how these technologies can enable deep decarbonization. These two projects are designed to complement each other and help us clearly understand today's impacts and other explores realistic options for the decarbonization of the cement in the future, and it's very important for the net zero objective to 2050. The section will conclude with a short closing address by Silvia Meirelles, our President of Board of Directors of C5 Lab, followed by the Q&A session. To open the session, it is a pleasure to introduce Professor Paulo Ferrão, a distinguished professor of Técnico and the president of EN+. He was one of the architects and the fathers of the collab model in Portugal and a driving force behind this success. His work continues to inspire collaborative action on smart cities, sustainability, circular economy, and public policy in Portugal and in Europe. Professor Paulo Ferrão, the floor is yours.
Thank you very much, Margarida. So thank you very much first for your very kind words and for inviting me. I would like to say good morning to all present in this session. And indeed, before I elaborate on the session content, I would like to start discussing the collaborative laboratories or collabs model, indeed in which origin I had the pleasure to be involved. Well, in Portugal, the collab model was designed to bring together companies and research units into a shared structure with a clear purpose to create a qualified scientific employment in Portugal through research and innovation agendas that generate economic and social value and that tackle complex and large-scale problems through real collaboration between academia and industry. It is certainly a structure built for a shared ambition and shared delivery to add economic and social value. Basically, we are speaking about companies that were created in a joint venture between the industry and the research labs. So this brings me to C5 Lab, which is the co-lab focused on innovation to decarbonization of the cement industry. And within that mission, we are today discussing Action Line 8, which is an interdisciplinary task force dedicated to sustainability modeling for the cement and concrete industries, as Margarida just mentioned. So position within the stock from source to carbon sink. So today, we close two key projects from that effort, AL 8.1 and 8.3. And I would like to recognize the teams involved, to which I had the pleasure to contribute, which included members from the industries, engineers from the industries, colleagues from academia, and in particular, Melissa Bacatello and Francisco Capucha, which have developed their PhD thesis in this context. Well, and not surprisingly, cement was the focus as the backbone material of concrete, which indeed constitutes a large part of the building and infrastructure we all depend on. At the same time, cement manufacturing is CO2 intensive, and a significant share of the emissions arise from the chemical reactions which compose their manufacturing. So, if we are serious about decarbonization, we need two things at once: credible measures to detail where we are, and then a credible research pathway to provide the vision for the future, for where we can go. And this is exactly what the Action Line 8 is about. And the easiest way to understand today's project is as a pair, as a couple. So project 8.1 is about where we are in Portugal, so to characterize the emissions in the Portuguese factories. So, and with this, it creates a shared, standard-aligned baseline for the Portuguese cement sector, so that decisions can start from the same reference point. Here, it is very important to mention also the role of ATIC, which indeed brought together data from the industries and provide all the data that make this study possible. And then 8.3 is about where we want to go, where we can go. So it asks what becomes viable when combining CO2 capture with green hydrogen. And then, and when we assume and assess pathways with rigor, not enthusiasm, we have 8.3. So let's look at 8.1. So it delivered the life cycle assessment model for the Portuguese cement, built as a cradle to gate eco-profile, and paved the way for environmental product declarations. Indeed, one of the milestones was the first environmental product declaration for Portuguese grey cement, based on the LCA model and independently verified and validated. This was a teamwork, again, led by Capucha, which will present the work next, but again, which brought together all the colleagues and engineers from industries and academia. And here is the key point. In a sector where scrutiny is rising, independently verified environmental product declarations change the quality of the conversation. They moved us from we think we can demonstrate. They give industry a credible reference for disclosure, and they give the wider ecosystems a basis for trust and comparability. So, what did Project 8.1 deliver in one sentence? It delivered a credible, standard-aligned baseline for Portuguese ordinary Portland cement with the structure needed to support independently verified environmental product declarations. That's, in fact, to state where we are in Portugal. Now, Project 8.3 started from here and began with a question that is simple to ask, but very hard to answer properly. So this is basically, what about if we capture CO2? And what if we could use it in a way that meaningfully changes all the manufacturing system? So Project 8.3 approaches this question through a combined lens, techno-economic assessment and life cycle assessment, supported by a multi-criteria approach for comparing different alternative models. The approach was to look at models that integrate CO2 capture with green hydrogen, with the goal of selecting a viable pathway and validating it through a structured assessment. This pathway is highlighted in the work in a closed-loop model described as the circular Portland cement concept. Circular Portland cement concept. The term closed loop matters because it signals a move from incremental optimization to system redesign. It is about linking the flows so that the overall model becomes more circular by design. In this concept, the CO2 released is captured and converted by adding the hydrogen into synthetic natural gas and oxygen from the electrolysis to produce hydrogen. And all of this is reused, reinforcing the closed loop logic rather than treating byproducts one of the other. And this is where we can go. So now let me bring to the pair together, because this is the message I want to land in the room. AL 8.1 makes the present measurable and credible. It gives us a baseline for the Portuguese ordinary Portland settlement that is cradle to gate. And it supports independently verified environmental product declarations which were produced. And then Project AL 8.3 takes the future seriously. It explores a circular redesign that links CO2 capture with green hydrogen, and it tests a closed-loop circular Portland cement concept in which CO2 is converted into synthetic gas and oxygen from electrolysis is used in an oxy-fuel combustion. But it was also made possible because industry experts worked with academia to share and advance knowledge. And this is really the great virtue of the collab. And that's where the C5 lab specifically deserves real emphasis. The collab framework exists to connect institutions and stakeholders around agendas that create economic and social value, and to do it through sustained collaboration that can tackle complex changes. And indeed, today you will see this is not a slogan. It is the mechanism that turns good analysis into credible disclosure and credible concepts into innovation pathways that can be tested and carried forward. I believe this is perfectly demonstrated in Action Line 8, operating with the scope of the C5 lab activity. So today is a closing, but it is a handover. So the baseline from AL 8.1 is something we can build on. The circular direction from AL 8.3 is something we can continue to test, compare, and refine. And the collab structure is what matters to those two things stay connected in practice. So I believe, and I'm very happy that we are today witnessing a very, very interesting project that really matters and that really is, in the end, the objective of the collabs. So I would like to hand over to Melissa, that we will go on with the technical issues and to wish you all a great session. Thank you for inviting me.
Thank you for the introduction, Professor. Environmental-related challenges were the driving force for the European Green Deal strategic vision. It aims to achieve net emissions of greenhouse gases by 2050. However, there are industrial emissions from sectors that will be hard to eliminate. The manufacture of cement is a major contributor to climate change, as it is a CO2, energy, and material-intensive industry responsible for around 7% of global anthropogenic CO2 emissions. Around 60% comes from the calcination of limestone, which is essential for producing clinker, the main cement components, while the remaining 40% results from fuel combustion in the cement kiln. Sorry. To reflect on this challenge, think about it. Is CO2 a friend or foe? Regardless of the answer, did you know that concrete, which is made from cement, is the most widely used man-made material on Earth? Concrete is vital for a modern world. It underpins our society, providing everything from our homes, transport networks, and the hospitals that we need to thrive. Its strength and resilience make it the ideal building material, essential to meeting the demand for critical infrastructure as our global population grows and continues to urbanize. So, the industry faces two challenges: drastically reduce CO2 emissions to reach carbon neutrality by 2050, and reduce dependence on volatile fossil fuels while staying economically viable. To face this challenge, 5 key entities in Portugal joined forces to accelerate the decarbonization of the cement and construction industries. This partnership unites the only two Portuguese cement producers, Cecil and Simpor, with the Technical Association of the Cement Industry, ATIC, Instituto Superior Técnico, IST, and the National Laboratory of Civil Engineering, LINEC. Together, they created C5 Lab, the Sustainable Construction Materials Association. It's a collaborative laboratory and R&D platform focused on developing innovative technologies to reduce the CO2 footprint in the production of cement, mortar, and concrete. This partnership bridges science and industry, ensuring that research leads to real scalable impact. Our name reflects that spirit. The 5 stands for both our 5 partners and the 5 C pathways where emissions can be reduced across the entire value chain: construction, concrete, cement, clinker, and carbon capture. A complete roadmap for decarbonizing cement. Across these 5 areas, we tackle every opportunity for transformation. It begins with construction using technologies like 3D printing of concrete. We can also use captured CO2 to produce concrete with recycled aggregates and replace transportation with lower carbon alternatives. In the cement stage, the focus shifts to clinker substitution and the adoption of renewable energies. In the production of clinker, there's a potential to reduce emissions, namely through the use of alternative fuels such as scrap tires. These 2 pathways are further explored in the 8.1 project. However, carbon capture, utilization, and storage, CCUS, is an indispensable solution with the potential to reduce up to 42% of remaining emissions by storing it or transforming CO2 into usable fuel, for example, contributing to the industry's energy independence, as you'll see in Project 8.3. At C5 Lab, all our work aligns with this vision through 3 core research areas, starting with CCUS. We're not just capturing CO2, we're giving it a second life. Our teams are developing processes to convert captured CO2 into synthetic fuels like methane or methanol. The second area is all about energy transition and efficiency. We optimize grinding processes, improve heat recovery, and replace fossil fuels with green ones. And the third area focuses on novel cementitious materials for sustainable construction. We're rethinking materials from the ground up, developing eco-efficient concretes that use secondary raw materials, alternative binders, and recycled aggregates. Using life cycle assessment, we can evaluate each material's true environmental footprint. Together, these three areas turn a centuries-old material, cement, into a platform for innovation. In our daily work, we combine a wide range of skills to accelerate sustainability in the sector, from consulting, including environmental product declarations, to research and innovation projects. We carry out in-depth analysis in our lab, and we implement these activities with technical training, empowering teams to implement sustainable practices. In fact, Francisca Pucha is now going to present the 8.1 project of Action Line 8. The floor is yours.
Thank you, Melissa. Good morning, everyone. I will now talk to you concerning Project AL 8.1, which concerns the life cycle assessment model for the Portuguese grey cement. This project has two main objectives. The first was to develop a high-resolution life cycle assessment model for the grey cement production within Portugal, which will then be used to produce the very first environmental product declaration for cement to be published in Portugal. This project was supported by a multidisciplinary task force composed of human resources from all consortium members of C5 Lab, including both cement manufacturing companies, Cecil and Simpor. The project motivation is rooted within European Union Green Deal and its intention to achieve carbon neutrality by 2050. Being responsible for around 5 to 7% of total anthropogenic emissions, the cement industry faces a major challenge in terms of decarbonization. It has therefore established its own roadmap for achieving carbon neutrality, and this project is part of that endeavor. The research strategy was divided into three main pillars, all established on a baseline cement life cycle assessment model. The first two are related with Project AL 8.1, and the last is concerning Model AL 8.3, which will further be explained by my colleague Melissa Bacatil. The first pillar assesses the current state of the Portuguese cement industry. This is based on the results of the main life cycle assessment model, and then also had the parallel objective of publishing the first environmental product declaration. The second pillar uses the structure of the base model to study the impacts of industrial symbiosis measures, namely the use of alternative raw materials, alternative fuels, or clinker substitutes. It aims to study the feasibility of the ambitions for the year 2030. The third and final pillar uses the base model to develop a proposal for an alternative post-2030 scenario. This combines carbon capture with the production of green hydrogen for the synthesis of synthetic natural gas to be reused as fuel. Life cycle assessment is a powerful tool that examines the environmental performance of a product throughout its life cycle. Its implementation is divided into four interconnected phases. We have the goal and scope, which establishes the context in which the analysis will be applied. We move to the inventory analysis, which identifies and quantifies the inputs and outputs. Then we have the impact assessment, which calculates and quantifies the effects of those inputs and outputs calculated in the inventory. And finally, interpretation, which, as the name implies, interprets the results. In addition, the boundaries of the system study also follow some principles, named the principle of modularity, whereby processes must be assigned to the module where they occur, and the polluter pays principle, whereby the impacts of waste are attributed to the system that generates it. The main life cycle assessment model is a cradle-to-gate study whose declared unit is 1 ton of Portland grey cement, and it was prepared in accordance with standards, namely standard EN 15804, which is the standard for producing environmental product declarations. Being a cradle-to-gate eco-profile means that the model covers information models from A1 to A3. This means A1, raw material extraction, A2, transport to the manufacturing site, and A3, the manufacturing itself. As for the selected system boundaries, the geographic boundary is located within mainland Portugal. The reference year chosen was 2018 because the project started in 2020 and for reasons of industrial confidentiality, only data that is 2 years old could be used. Finally, it should be noted that there is a great deal of technological homogeneity as all manufacturing units use the same production method, which is the dry process. In order to properly model the life cycle of a product, the life cycle assessment analyst must understand the entire manufacturing procedure. For cement, it starts with the procurement of raw materials, being them either primary or secondary with either external or internal origin, followed by the transportation of these raw materials and also fuels to the manufacturing site by either freight transport or conveyor belts in the case of the internal quarries. As the raw materials arrive in a manufacturing facility, they will enter a mill denoted raw mill in predetermined fractions where they are milled to prepare them for the next step, which is the rotary kiln, and within it, temperatures reach up to 1400 degrees, occurring key reactions with particular focus on calcining, which you can see down there, that create the intermediary product clinker, which is the main constituent of Portland cement. After cooling, the clinker enters the cement mill, where, together with predetermined mixtures of additives, it is milled to produce the desired cement blend. The following diagram shows the division between foreground and background processes within the LCA model. All processes whose producers have direct influence, such as internal extraction processes or the rotary kiln activity, are considered foreground processes. These are modeled using primary data obtained directly from the producers. It should be noted that for the modeling of this model, we considered electricity generation to be foreground, even though producers have no direct influence over it, but it's such an important process that it had to be modeled using primary data. For the background processes whose producers do not have direct influence, such as the production of additives, the generic data was used, and this generic data is usually referred as secondary data. All primary data is based on industrial statistics from the 6 factories. As for the secondary data, it was obtained from Eco Event 3.9.1 or other EPDs. The primary data was collected in collaboration with the Portuguese cement industry, represented by ATIC, Cecil, and Simpor, on behalf of C5 Lab. However, industrial confidentiality required the consolidation of data. Therefore, in collaboration with the industry, an automatic consolidation sheet was developed to allow data to be provided anonymously. With all data collected and consolidated, there's then the need to process it to be suitable for the LCA software. And in order to process the data, an automated spreadsheet was programmed to calculate the flows according to the declared unit, preparing the data for its input into the lifecycle assessment software, which in this case was CIMA Pro. Once the manufacturing process is known and the entire inventory data is provided, the life cycle assessment analyst creates flowcharts to guide them to produce the manufacturing procedure. The following diagram illustrates the flows associated with model A1, which is concerned to the extraction and processing of raw materials. Here you can see the flow of raw materials need to produce one declared unit. There's been 1 ton of ordinary Portland cement. Since the reference year was 2018, we used the energy mix for that year, and we obtained this information directly from REN, which is the Portuguese entity responsible for the handling of electricity. As for this diagram, it shows the flows of the rotary kiln activity, which is still related with model A1. Here we can see the energy flows and fuel flows and emissions associated with the production of one declared unit, so the amount of energy that is required to produce one ton of Portland cement. As for these tables, they show the average transport distances for raw materials and fuels. This corresponds to model A2. These average values was determined with the help of industrial experts from our team. As for model A3, it corresponds to the manufacturing procedures themselves for the products. This diagram, for example, it illustrates the flows necessary for the manufacturing of the intermediary product clinker in a sufficient quantity for the production of the declared unit, which can be seen in the following diagram. Waste is generated throughout the whole production chain, and so the management of this waste is also modeled throughout the production, and you can see here in this diagram the production of waste and its management. And finally, we have the following chart, which depicts the entire manufacturing chain. This is the entire model that was inputted into the LCA software. It is all the flows that are necessary to produce 1 ton of the average Portuguese grey cement. This was modeled in the software CIMA Pro and includes all flows necessary. After the introduction of the data into the LCA software, this computer model was run to obtain the results which we observe here. The impact assessment was carried out in accordance with the criteria of standard EN 15804 using all available environmental categories, including the optional ones. And we can observe that the rotary kiln activity has the highest impact contribution to the majority of indicators, with special relevance to global warming potential, where it contributes with over 90% of the impacts, which is mainly due to the calcining reactions that occur within it, but also the fuel combustion reactions. This was then followed by electricity consumption, which is also highly relevant in some categories, such as freshwater eutrophication or acidification, concluding that energy consumption, together with calcining, is the major contributor to the cement environmental profile. This is further supported by the carbon footprint, where it's clear that the activity in the rotary kiln, so the fuel combustion and the calcining reaction, has by far the highest contribution, followed by electricity consumption, with all remaining processes contributing only around 1%. The trend continues when analyzing the primary energy depletion, where it's possible to conclude that the rotary kiln depletes over 2.3 gigajoules of non-renewable energy. This model does not consider the procurement of alternative fuels, because due to the producer polluter pays principle, they are excluded from the model. This is then followed by the electricity generation, which depletes around 1 gigajoule. However, due to the high incidence of renewable energy in Portugal electricity mix, around 70% of it is considered renewable. As for waste management, cement manufacturing is a highly efficient and mature industrial process, whereas around only 6 kilograms of waste are generated per ton of cement produced, and over 91% of it is valorized. either internally or externally. In parallel, we also conducted a benchmark against some of its peers, concluding that the Portuguese average cement is equivalent to a European average CEM2 cement. This is noteworthy because the Portuguese average cement includes the production of cements with high clinker content, such as CEM1, whereas CEM2 is a blend with a lower clinker content. So we are equivalent to that. We move now to the second pillar of Project AL 8.1, which concerns industrial symbiosis targets for the roadmaps of decarbonization. Industrial symbiosis is a relationship in which, instead of eliminating waste generated by an industrial process, it is then redirected to other industries. The measures selected are based on strengthening the application of existing techniques based on the principles of circular economy, namely alternative raw materials, alternative fuels, and clinker replacement. In addition, to reflect measures that may indirectly impact resource use, the effects of energy efficiency were also studied. Cumulatively, these measures are expected to result in a reduction of about 166 kilograms of CO2 per ton of cement produced on the year 2030. So we introduced this data into the new model, and the results for the alternatives scenarios based on the industrial symbiosis showed that the use of alternative raw materials and clinker substitution resulted in a reduction of the carbon emissions. However, the use of alternative fuels led to a slight increase in emissions. This was unexpected, and this increase was due to the fact that at the time, the modeling technique accounted for the biogenic emissions, so they contributed with for the environmental impact. And this is not currently used in cement manufacturing life cycle assessment models. Therefore, the results will be a bit different nowadays. The replacement of clinker produced the most significant reduction due to the ambitious target of 65% average clinker content. And finally, we can also conclude that the inclusion of energy efficiency measures further amplify the reductions observed. When examining the variations in CO2 emissions, the effectiveness of clinker substitution can be observed, thus confirming the importance of controlling this ratio as the most important measure and most effective measure within the cement industry, otherwise than carbon capture. We notice also that counterbalancing effect of the use of alternative fuels caused by the increase of biogenic emissions. However, with the new standards for assessing the environmental impact of cement, nowadays the alternative fuels used would actually produce a more robust reduction, so the results will be even more amplified nowadays. Finally, a standardized comparison was made between the study results and the cement expectations for 2030 to assess its feasibility, and it can be referred by the results that they are in line with the industry expectations, with only a slight higher impact than expected. So we therefore confirm that the industry expectations, so what is in the roadmap for ATIC and Cement Europe, are realistic and can be enforced. Now we move to the second goal of Project AL 8.1, which was the development of the first APD for Portuguese cement of them all. An APD, or Environmental Product Declaration, is a document registered and verified by an independent entity that communicates information about the environmental impacts during the life cycle of a product in a transparent, comparable, and credible manner. It declares the environmental performance of a product based on the life cycle assessment models, with all information being verified by an independent entity, which guarantees then transparency and enables an unbiased comparison of products. Since the results are pre-verified, The environmental product declarations allows for a safe comparison of equivalent products across multiple databases. This avoids greenwashing as all results must be validated before publishing. In addition, since the EPDs are sourced from highly detailed life cycle assessment models and they are verified, it allows throughout the years to evaluate accurately the effectiveness of the environmental roadmaps of any sector. There is a growing demand for building certifications such as LEED or LEED, and these often require environmental information that could be available from environmental product declarations, and without them, generic data may be used, and this could negatively affect results because generic data tends to be more conservative. Moreover, there will be an increased integration of environmental information in documents, such as the declarations of performance, whose data can be also obtained for environmental product declarations. Therefore, companies that already implement environmental product declarations will be better prepared for its integration in such documents. In reality, starting this year, the global warming potential will be mandatory to be part of the declaration of performance, followed by a European mandate to perform life cycle assessment for buildings over 1,000 square meters in 2028. In 2030, not only additional indicators such as acidification will be added to the declarations of performance, but the life cycle assessment will be mandatory for all building sizes, finalizing in 2032, whereas the declaration of performance will essentially fuse with EPDs, and all information currently on EPDs shall also be present in the declaration of performance. In conclusion, the market demand for EPDs is steadily increasing, and it's being fueled by the increased interest in voluntary sustainable building certification by clients, the LCA of buildings becoming mandatory, the inclusion of environmental information in the declarations of performance, culminating with the introduction of the digital product passport, which will require information available in EPDs. EPD demand will only accelerate in the following years, and AL 8.1 positions the cement industry in the future by providing with an environmental product declaration which solidifies its stance and commitment to reach carbon neutrality. If you're interested, you can consult the first EPD here in the following QR code. AL 8.1 had a substantial contribution to the Portuguese cement industry, including a confirmation that it already overperforms environmentally, being equivalent to the European CEM2 and 26% less impactful than the average Italian cement, with results being externally validated as its EPD was verified by a third party. The project was also able to confirm that the industrial symbiosis measures led to a result of 23% decrease on its carbon emissions, being able to validate ATIC's carbon neutrality roadmap. The work of AL 8.1 resulted in 2 scientific publications, which I invite you to read by accessing the following QR codes. To conclude, AL 8.1 also produced more added value to the sector, namely 1 PhD thesis with a life cycle assessment model of cement manufacturing, 4 scientific communication actions, over 18 scientific reports, and since the genesis of the project, over 20 environmental project declarations have either been published or submitted by C5 Lab, proving that the effectiveness of this project in continuous of generating the know-how in EPD development. Now I pass the torch to Melissa Bacatel, which will talk to you about Project AL 8.3. Melissa, the floor is yours.
Thank you, Francisco. So far, we've been imagining the world up to 2030. But what if we could capture that CO2 before it was even emitted into the atmosphere? Since the CO2 emissions are intrinsic to the cement manufacturing process itself, it's particularly interesting to explore how we can capture these emissions. Imagine the cement factory emitting CO2. We can capture that CO2, combine it with hydrogen produced from renewable energy, and convert it into methane. The methane is then fed into the natural gas system to which the factory is connected to. And then we have a closed loop that recycles CO2. So the aim of the 8.3 project was to design and analyze the techno-economic and environmental viability of such an alternative cement model. This promotes not only cement decarbonization, but also circular carbon economy, the factory's energy independence in an economically viable way, with a long-term vision towards 2050 at an industrial scale. The methodology was divided into 4 parts. We began by characterizing the case study to create a data benchmark for the next phases. Next, we compared 3 CO2 capture technologies through a multi-criteria evaluation that covered technical, economic, and environmental considerations to select the most feasible one. The selected CO2 capture technology was then integrated into 2 proposed alternative cement production models, which constitutes the third part of the research. And finally, we carried out a life cycle assessment comparing conventional production with the selected innovative model, also analyzing different renewable energy sources. We started by characterizing the Portuguese cement industry. Next, we compared 4 CO2 capture options based on techno-economic and environmental criteria. An option with no capture, monoethanolamine, calcium looping, and oxyfuel. The system boundaries were cradle to gate across 3 future scenarios. We calculated mass and energy balances and accounted for economic uncertainties due to the low maturity of these technologies. We assessed economic performance using indicators like the net present value, which we aim to maximize. We also looked at the internal rate of return and the payback period. To assess the decarbonization potential, we compared CO2 emissions of each alternative. They are lower for calcium looping, however, oxyfuel requires less energy. We also rated retrofitability based on cement quality risk, space constraints, safety issues, and technology maturity. We built a normalized matrix across technical, economic, and environmental categories. Calcium looping rate scored highest in most scenarios, and this work was published in the Journal of CO2 Utilization. You're more than welcome to scan this paper. Therefore, calcium looping moved on to the third research phase, where we compared 3 cement production models across 3 scenarios. First, the business as usual. No capture, no reuse, that's our baseline. Then, the circular model, where we capture the CO2 emitted by the clinker kiln and use water electrolysis to produce green hydrogen and oxygen too. That oxygen doesn't go to waste. It powers the calcium looping CO2 capture system. Then comes the cool part. Hydrogen and CO2 react to create synthetic natural gas. And that gas, it fuels both the kiln and the capture unit. A true circular CO2 loop. In the hybrid model, things shift a bit. Hydrogen is transported through a dedicated pipeline, so there's no electrolysis on site, which means we need an air separation unit to produce oxygen. The CO2 is still captured and converted, but the methane is sold, not reused. So, which model gets us closest to our goals? To answer that, we broke our analysis into 4 pieces: economic performance, technical feasibility, decarbonization potential, and finally, eco-efficiency. I won't get too technical here, but we ran full mass and energy balances using primary and secondary data. On economics, we looked again at the NPV, and it changed a lot depending on the scenario. In the best cases, both the business as usual and circular models were viable. But in the worst, none were. The internal rate of return favored the business as usual in an ideal scenario. But in more realistic conditions, circular takes the lead. And how fast can you get your money back? No surprises here. The shortest payback happens in the reference case. The environmental analysis revealed that the circular model can reduce CO2 emissions by up to 98%. And even the hybrid model shows a significant reduction of 91%. But it comes at a price. The primary energy required for the circular model is 15 times higher than the reference, while the hybrid model is around 7 times. In terms of technical performance, the alternative models obviously have a lower technology readiness level than the business usual, but they present a higher energy independence. To understand eco-efficiency, we merged emissions data with cost analysis. And here's the twist. Selling surplus methane and oxygen makes the circular model look even better. The multi-criteria analysis revealed that the circular model ranked highest overall. Following on from this research, a second paper was published in the International Journal of Hydrogen Energy. Again, please scan this paper. With the circular model selected, we moved to the fourth and final research phase. Our final goal was to analyze the circular model's environmental performance using the same standards applied to construction products. We looked at key impact categories. I'm talking about climate change, eutrophication, resource use, and others like acidification or water use. We ran 2 models in CIMAPRO and tested 3 energy sources for electrolysis: solar, wind, and a mix of both. This leads us to our final research question. Is the circular model truly more sustainable? We broke this question into 3, starting by comparing the environmental impact associated with the circular model and the business as usual, tested different renewable energy sources, and found the environmental hotspots. The mass and energy balances were adopted to CIMAPRO, and the results show that the circular model can reduce the impact of climate change by up to 68% in the wind scenario. And the hotspot analysis revealed a negative impact for fossil resource use, thanks to credits from avoided natural gas extraction through methanation. But here's the catch. Electrolysis had the highest environmental impact in all categories. And where does this impact come from? Mainly from the extraction of raw materials, some of which are rare, to produce the components of solar panels or wind turbines, although the impact of turbines is lower. In short, while the circular model offers major benefits, it also presents some trade-offs compared to the conventional model. A paper based on these findings was also published. This work involved at least 1 representative from each of the 5 C5 Lab associates. We also had the special contribution of Paulo Rocha and Alfredo Cardeiro in developing the decision support tool. So now let's see if we achieved the goals. First of all, the circular model reduces net emissions by up to 98% compared to the current model, converts 90% of captured CO2 into synthetic natural gas, and reuses 100% of the oxygen from electrolysis, thus contributing to the circular economy. In addition, it increases energy independence, and now we have 2 new sources of revenue through the sale of surplus synthetic natural gas and oxygen. This makes it an economically viable model, except in the worst case scenario. This project resulted in 1 PhD, 2 awards, 1 national and 1 international, and 3 papers. 4 deliverables, 7 scientific events, and we produced a total of 19 reports. I hope that throughout this presentation, you have found elements to reflect on the question I posed at the beginning. Do you consider CO2 a friend or foe? The answer, as you can see, is not linear. It's actually circular. CO2 can be a challenge, but it is also a valuable opportunity within a sustainable circular system. Thank you very much for your attention. I'll now hand over to Cecilia Meirelles to close this session, and then we can move straight into the Q&A.
Well, hello, good morning to you all. I hope you're listening. You're able to listen to me, to hear me. Okay. I'd just like to give a brief thank you to all of you that were with us here today in this webinar from the C5 Lab. The C5 Lab is very important for the Portuguese Cement Association, of which I am Secretary General. And of course, here in the cement industry in Portugal, we are absolutely committed with decarbonization, and that is our main goal. And that is a huge task ahead of us, and we know we can only fulfill it with knowledge, innovation, and the academia. So C5 Lab is like all that coming into flash. So it was a pleasure to be here in this webinar. I hope it was useful for you, and many thanks to you all. So, and now I believe we can close the session and go to the Q&A.
Thank you, Cecilia. Yes, we have a question here from José Condens. Hello, thanks for the nice presentations. I have a question to Francisco Capucho. Can you explain more about the digital passport? What does it consist exactly on?
Sure. Thank you for the question. So in essence, a digital product passport will be a structured, readable, machine-readable record of a product. So it's like a document that has all essential information from that product for the full life cycle, from production to its end of life. It includes information about its batch, core product and manufacturing data, material and composition details, its performance, compliance documentation, and then with some links such as environmental product declarations and certificates of sustainability. Therefore, it's a document that puts together all the information of the product. Essentially, is a like an ID for the product, and it will have a big part of it will be environmental information, and therefore that's why I talked about it in my presentation, because part of the data that we use on the digital product passports for the environmental and sustainability assessment can be obtained from the environmental product declarations, because they are more or less related. The same with the declaration of performances, because there is also this effort within the European Union to make everything on the same platform and using the same rules, which is more or less based in the standard EN 15804. And so essentially is this, it's an ID for the product with all the information there that is traceable. I forgot to also say that traceability is a vital part of it, and we as C5 Lab, we can contribute it not only in other parts but with the information from EPDs. Thank you for your question.
Thank you, Capucha. Let me just add that these DPPs, so the digital product passports, are standardized digital records that travel with the product across its life cycle. So they store information like what it's made of in terms of materials, where did it come from, what is the origin of the materials, the supply chain, the production data, how can you use and repair it? So when it comes to the maintenance, its sustainable footprint, not just in terms of carbon, but also other indicators and the compliance, and also how can you recycle the disassembly instructions and end-of-life routes. The goal here is to make products more transparent, repairable, and circular, and to support compliance and reporting across value chains. I hope this clarified your question, Jose. So if no one else has a question.
If I can make a question to Professor Paulo Ferrão. Thank you very much for these 5 years with us, and I want to question how you see the future of the collabs and the future of these kind of lines for industry, because it's very important from the part of the academy and your part that you are so interlinked with academy and industry. I think it's a good way to end this session. Thank you very much, Professor.
Thank you, Margarita. Well, my answer is very easy. I think the collab in your hands will have a good future. And what am I saying? What I see here today is really the industry. So in this case, Simpor and Cecil, and represented also by ATIC, the association, working really very closely with the collab. And then the collab incorporates other partners from academia. And the essence of the collab is that the collab can provide particularly services to the industries. And what we saw today is a wonderful demonstration of that. So the industry, for example, in this case, when they wanted to have the environmental product declaration, they asked it to the collab, not to an external consultant. And indeed, they had a very good outcome of that. Of course, very well supported, and it is indeed very important. So that the collab with the people they have, with these wonderful PhDs that have been presenting today so well, are then providing services to the industry, but also to other industries that might request their service. So I'm so happy today. It's a very happy day for me as well, because indeed I see the collabs, and in particular this collab going on. They are hand in hand with the industry. Well, they are run by industry, and this is very important. And that was the spirit of a collab. So first of all, to you, Margarida, as the director of the collab, I would like to congratulate and to wish you, of course, the best. And indeed, the future in your hands, and certainly in very capable hands with all these wonderful team.
Okay, Professor. I think it's a good way to end the session. Thank you very much for all the presentations, for all the effort here, and I think I will hope that we'll see soon with another webinar about another subject that we have in our collab. Thank you very much to all. And thank you very much for attention of the public. Good morning.
Thank you.
Thank you.